So this is Jack. I'm from the PyTorch X-ray team. Today, I want to give a brief overview of how do you debug a PyTorch X-ray program. After watching this video, you should have some basic understanding of how PyTorch X-ray works, how the execution looks like, how to collect profile, how to tell whether there's a graph breaks, and like how to understand a profile. So let's get started. So I actually just create a new container. And I git clone the PyTorch X-ray repo because I need some examples. Let's first install the PyTorch X-ray. So I am going to use a nightly version, but you might want to use a release version. So what you want to do usually is go to the PyTorch X-ray repo, like this under PyTorch/X-ray, and then go to a README. The getting started usually have the most up-to-date instruction on how to install the latest release. But for today's purpose, I am going to use the nightly, which is in available Docker image and will, like we have a list. My Docker is Python 3.10, so I am going to copy this. By the way, I'm using VS Code. It actually makes a lot of things easier. I will show you why. So first pip3 install. So the link we post is for the PyTorch X-ray, but actually if you just remove the X-ray, it's going to install corresponding PyTorch nightly as well. So let's see. Successful install. Okay. Then just go back here and add the X-ray. And also, the PyTorch X-ray project is available for both like CPU, GPU, and TPU. But for today's purpose, I am going to use a TPU as example, and the profile part is going to be a TPU profile as well. I am currently on a TPU v48, which means I also need to install libTPU, which is also one command you need to run under a variable Docker image if you install it nightly. Yeah, because I actually already installed in this machine, so it doesn't do anything. So what I usually want to do is I usually want to run a quick sanity check before I do go any further. So let's import torch. Oh, that's typo. And I import torch X-ray. And then torch.version. It shows 2.4 because today is June 5th. And the 2.4 has not been branch cut. So our nightly right now is 2.4. Okay, so it seems like the version is correct. Let's try to get a device. Okay, also return device. If there's anything wrong with the libTPU version, like this is the step where you usually throw error. So this means like the sanity check is complete. And let me quickly walk you through a very simple PyTorch X-ray program. So what is the template? So let's say you initialize the torch.random 5 by 5, and then you move it. Let's just do a device. To device. So now what you can do, you can print a T1.device. It should tell you it's on X-ray 0. So let's say you have T2 equal to T1 times T1. And then T3 equal to T2 plus 5. It's a very, very dummy example. And let's set a breakpoint here. Okay, let's run this example. Stop. Oh, I forgot to say. Here we go. Oh, okay. This is a problem. Like I shouldn't, if I install nightly, I shouldn't run anything under X-ray. Otherwise, you will try to use a local torch X-ray instead of the system installer. Let me try again. Stop. Let me just move this out. Move transport time. That's like annoying, but let's see. Okay, it's here. So it prints the T1.device, which is X-ray 0, which makes sense. And then we execute some operation. Okay, so here's the first thing I want to talk about that's different about the Torch X-ray. So Torch X-ray is based on, it's under the hood, it was connecting to the Google's X-ray compiler. And that's the only way you can run anything on the TPU. And the structure of the Torch X-ray, it looks like an eager program because like you step through, everything just works as expected. But what's really happening here is that we usually call this part tracing. So when we actually executing this T1 equal to T1, T2 equal to T1 times T1, and T3 equal to T2 plus 5, we are not actually executing anything on the device yet. So what we do is something called tracing. So we are constructing a graph. So that takes some input. In this case, the input is a T1, which is a 5x5 tensor, and you actually have two output. The output is T2 and T3. And then at this point, like none of the device execution is being done. We just created a graph. You can just print, like you can print a T2. It's actually going to execute a computation. I will show you how. But the more recommended way is for you to run all of your computation code all together, and in the end, you do a right now we call torch x-ray.sync, but if you're using a nightly, it's called xm.markstep. They are the same thing, we just kind of rebranded. So it's in the import torch x-ray.core.x-ray model as xm. So this markstep or torch x-ray sync, like they are the same thing. What they do is like they take all of the accumulated computation and they execute it. So then after this point, like all of the value is being computed. Another thing I want to call out is like the X-ray compiler will try to compile the program upon the torch x-ray.sync or the mark step. And the compilation step might take a while depending on how big is the program. But you only compile once for the same program. So which is usually means for torch x-ray, the first step is usually a bit slower than the following step. But as long as you don't have any dynamic shape problem, so all of the shape of the input is the same, the computation is the same, ideally you should only execute once. Okay, so I talked about a lot about what exactly happening. So it's kind of difficult to imagine or visualize what's happening. So which is why I am going to introduce a flag. So it's called PT X-ray debug equal to 1. So this flag is a variable since the 2.2 release, I believe. So just set this environment variable and then rerun and see what happens. Okay, it reached a breakpoint, doesn't do anything. Let's try to go a step further. X-ray doesn't. 1 second. Let's remove the breakpoint. Okay, X-ray debug open. Oh, wait. Here's the file. Oh, I know what's going on. I moved the file, but I still in the here. I still open the old file. Here we go. So we X-ray doesn't. No, this makes more sense. Open. Let's give it another try. This happens when you're trying to live recording. Okay, so let's take a look. So in here, it tells you that let's a compilation happen. That's because user mark step. Like I said, mark step and torch x-ray.sync is the one thing. So it tells you the graph input there are two, which I think one of them is T1. Another one I believe is 5, because 5 is a constant. We probably just wrap it around as a device data. And number of outputs 2, I think is T2 and T3. It's telling you the Python frame that trigger this execution, it's the mark step and then it's the sync. And under who is test.py, that's a 13, which is this line. So what does it really means? It tells you that in this line, that's the compilation is being triggered. And then on nightly, will also very nicely print a message telling you more analysis, like the graph inputs, how big is the input size, how is the output size, and how big intermediate tensor. Like this is tiny. Like when I show you a real model, we will see like this analysis be more helpful. And then the same graph is being executed. So PyTorch pt/xray/debug equal to 1 is a good tool to tell you, to give you a good idea of where the execution actually happened instead of like you're confused about which part is tracing, which part is like execution. So this is a very dummy example. Let's go to some more real example. So in the PyTorch X-ray, let me also show you here. Like under here, we have an example repo. Let's take a look of the ResNet. So this ResNet example, for the most part, is not PyTorch X-ray specific. I do use some of the helper tool in PyTorch X-ray to make a fake data, because for the purpose of this example, I don't need a real data. So you see here, the model is a ResNet 50, and I move it to the self.device, which is a Torch X-ray.device. And then what else is Torch X-ray specific? Oh, there's like PLM device loader. So this is parallel loader. This is a convenient data loader we wrap around the any PyTorch loader. It's also what we recommend user to do. Loss function is cross entropy. There's nothing special here. And then in the chain loop function, it's very standard that you get the data from the data loader and then you just run the model. So let me also open this in my VS Code. So it's in the examples chain ResNet base. Okay, it's a sensing. Did I modify anything? I didn't modify anything. Okay. Yeah. So you might be wondering, where is that Torch X-ray.sync or xm.markstep? You don't see here. Well, there are two things. First, for the purpose of this exercise, I think it's easier we do this. So make it very clear that first you trace the model, you get the loss, you run a backward, you run the optimizer, then the single step is finished. Then we run the sync. Then ideally, this sync should capture everything. The reason I didn't need to put Torch X-ray.sync is because we use the parallel loader. In the parallel loader, like by default, you will call the xm.markstep for the user, like for every batch you specify. But like I said, it's good to have when you know what's going on. But in the beginning, when you're starting to learn PyTorch X-ray better, you specify like Torch X-ray.sync directly. So now let's try to run this model and see what does it tell me. So PT X-ray debug. Actually, I'm going to use this PT X-ray debug level equal to 1. Actually, never mind. Let me do this. PT X-ray debug equal to 1 Python. You usually also want to set PGRT device to the TPU, but if you actually own a TPU, like this is by default, so I usually just don't bother. Example of X-ray, examples, chain, ResNet 50, ResNet base. Okay, let's see what happened. You also need to install the Torch Vision for ResNet to run. So let's see. So initially tell you let's mark step. This number of output is 53, number of input is 0. And this is in the next. This is the part I'm talking about. The parallel loader will call and mark step for you, but let's ignore this. This 53 is just because like all of the input data is fake. So I do believe like that we're just initializing a torch.run and using data. So what PTX-ray debug equal to 1 does is it's going to print a message every time that an execution happened and give you some information. But because I am actually using a VS Code terminal, it's actually pretty shallow. So Let me do PTX-Ray debug level equal to 1. So what this does is you only print the compilation helper message, doesn't print the execution. So it will be less verbose. This feature currently is only available on the nightly, but it should also be in the 2.4 release. For the 2.3 and previous release, you only have PTX-Ray debug to 1, which will be a bit verbose. So let's see. So here's the actual compilation. You see we're kind of stuck here, like let's normal output. Okay, just finish compilation. So this, I believe, is a real compilation. So you see you have the graph input, like 325 input and like 485 output. And the mark step is caused, as a compilation is caused by the sync. If you look at here, it's in the training loop 54. And let's see, where is the line 54? You see it's a touch of data sync. All right, great. What does it do? It's pretty much, it was just compiling the ResNet 50 forward, backward, and optimizer state. And if you look at the graph, the input is pretty small, output is pretty small, intermediate size is big. Like this is all of the activation, computation, etc. Yeah, then it doesn't print anything for the execution to be less verbose. So you see, for a typical program, you don't need to modify a lot of existing PyTorch. In here, like what we do, like we wrap the data loader around MP device loader. You need to move the model to the device, and then you need to add a torch.xray.sync or xm.markstep for every single step. For the most part, that's kind of what you need to do to get a single device training to work. I am using a V48. V48 has 4 chips. Each chip has a 2 gig HBM. So for this one, I'm not using the multi-device training. I can probably cover that in the next section. But yeah, like for single device, that's actually all you need to do. I believe the rest of this code, like they are not PyTorch specific. You can try the same thing on your own code. So what you should look for. So let me actually do one thing. That's one of the typical mistake people make. Well, let me make it a bit more obvious. So what people do is like if you are used to the PyTorch eager GPU, like many times you want to log like some of the information when it's available. Let's say, for example, the common thing what people do is they print a loss for every couple steps. But for the purpose of this, I just print once. There's nothing wrong with this, like if you're using the CUDA eager, but this is a problem for the PyTorch XPay. Because you see, like we expand this concept, we want to combine everything, the forward, backward, optimizer into a single step, and then the graph will be executed after this .sync. But if you try to print the loss before even the backward is being run, what ended up happening is that we do something called graph break. So it still works. So what happens like we finish the tracing of the forward of the model, and then we execute the forward because we need to resolve the loss, and then we execute the backward. And let's just run it again with PTX-Ray debug level equal to 1 and see whether that's the case. All right, let's see. The first one I can say, well, I think we're just syncing the data. And in here, it's something funny. Like you see, like the number of graph inputs 269. I think they are the ResNet 50's parameter. The number of outputs is only 1. And the trigger of this execution is this string in string, and it's in the ResNet 53. So it's here. So this is generally not ideal because for the compiler, the more a compiler can see, the better it is. Like it can better manage the memory, it can better fuse the graph to get better performance. For this particular case, that printing a loss is probably fine. You just break a single graph like into a 2 graph. And like ResNet 50 is relatively simple model, so it should still works. But for example, if in your code you have a lot of this logging for different tensor, they are just going to fragment in the whole graph too much. And for the PyTorch XPay to work the best, you want a single graph to capture everything. So let's just remove this. All right. Oh, it was just printing too much tensor. So you see, if you remember, the previous rate was around like the 1800, and right now with a print it becomes 1200. Why so much? This is because like it's another thing I want to talk about is like the tracing and execution overlap. So what happened, which I will show you more when I show you how to collect the profile and how to see the profile. What ended up happening on the host side is like we executing all of this Python code to trace the graph. And upon we call the torch xplay.sync, we construct a graph and see if we need to compile. If the graph is already been compiled before, we directly send this graph to the device for the execution. That execution is asynchronous, which means while the execution is happening, we start tracing the graph of the next step. So the graph tracing and graph like execution can be perfectly overlap. However, if you want to print something, you break that asynchronous. So the Python thread will be stopped until the execution of this value is complete. And then after we print value and then we start tracing the next part. Like in this, when you are tracing the next part, the device is pretty much idle. So that's why that's a very significant difference of the rate. We generally just want we just keep tracing in the Python process, keep sending the graph execution, which will get queued up, and then eventually it will get executed on the device one by one. So it might be a bit hard to visualize. So let me just collect a profile. So we actually have a tutorial on how to create profile, but in the example, I also have something relatively simple. So it's in the code example debug chain RESTnet 50 profile. Okay. So you see like the model is still the chain RESTnet base, which is what we use here. So it's the same model, but what this one do additionally is it's going to help you to collect a profile so you can better visualize like what's actually happening. So what do we do here? So let me actually just the temp profile and remove all the existing profile. Okay, this profile is empty. So, and let me just run this. And while it's collecting profile, I can explain what's happening here. Okay. So first we want to set some environment variable. It's actually better not to set it like in the code. I usually just manually set it in a terminal. So it's the same model. We first need to set up a profile port, and then we set up a profile log directory. So it will collect a profile, and the profile artifact will be put in this directory. It can either be a local directory, or you can also specify a JS bucket if you're using TPU, which means you are on the Google Cloud. Then the Google Cloud has a JS bucket. It's kind of just storage like on the cloud, nothing special about it. And you start a server. So server will be listening on the request to start profiling. Then, but what is actually start a profiling is this line called xp.traceDetach. What it does is it's going a separate thread. It will notify the server I'm starting collecting the profile, and theoretically it's going to collect everything happened in next duration second. I think is 30 seconds. And then after this time is over, then you should see the profile artifacts in the directory, and I will show you how to view it. To make this example small, I actually put it here, but ideally you don't want to put it outside of training loop. Usually what you want to do is if you go back in the training, what you do is you usually put it here. Well, then you need to redefine all of the directory. And you usually don't want to start profiling for step one, because step one is usually the compilation happens. Then a lot of this profile time is kind of idle, it doesn't collect anything. So it's usually step equal to 5, like something like this, you start a profile. But ResNet's simple enough, like you should see the profile, like well, the compilation is very fast, like 30 seconds should be enough. So now let's go to the directory. So where do we put the profiles? In the temp profile. Let's see. Okay. In the plugin, it's in the profile. Okay, so the profile is being collected. Let me show you how to visualize the profile. So you first need to install a TensorBoard. So you need to install the TensorFlow CPU and a TensorBoard. I think I already installed. Yes, cache. And then you just need to start the TensorBoard server locally, and then specify where the log directory is. Since you are running this on the TPU, you also need to set up the port forwarding. So then your XProv will the information will be forwarded to a local host. Then you can view this profile TensorBoard on your local Google Chrome, for example. But if you're like me, you use the VS Code. The VS Code is actually very conveniently set up the port forwarding for you, so you can just open it. Okay, so be slow. Let's go to the trace view. So you see like this, just localhost. And the port is the whatever port you specify on the command. All right. What exactly is happening here? Well, so the first couple things to notice first. There are a couple different bars here. The one you should pay attention is the top two. So top two is that TPU 0 and TPU 1. This is because I am on a TPU V48, and TPU V48 has 4 chips. Each chip has 2 cores, and each core is corresponding to like one of these. So TPU V4, it uses something called mega core. So pretty much it combines 2 TPU core into a TPU chip. So from user perspective, on the TPU V48, that's only 4 devices. But from the profile, you can see like that's actually 2 core. So this toolbar it show you like what is happening on the device side. And all of the trees below, as you can see, like there's a lot, but for the most part, you don't care too much about them. It tells you what happened on the host, so what's happening on the CPU. So what exactly happened? Well, all of this part, like you said, is doing the compilation. So this is happen on the step first. So when we first collect the graph and we kick it off for the compilation, it start the compile. And compile, you see, it takes a long time. If you go below, you also see like this part, but it's also marked step marker. Step marker is TorchXP.sync or XM.mark step. So during this mark step process, it's also trigger a compilation. Then where exactly is tracing? I think tracing is not shown here, but I believe tracing happens right before here. So yeah. Well, after I enable more flag, you can actually see how tracing is happening. But let's just go back to the device execution. What exactly is happening here? So you see here, like this is the device execution. Each single tab of this is actually one execution. Let's zoom in a bit. All right, it takes a while to load. And TensorFlow ops is just some annotation we add to notify to kind of make it easier to visualize what's happening. Okay, I realize this is a bit small. But for example, here's the A10 add, then it becomes a fusion. Like I think this one is convolution overridable. So this is a convolution of the like the ResNet. So this is a single step. What do we expect? In order to utilize the TPU, you expect a continuous execution of this graph. Like the more graph you execute without gap, it means like the TPU is not being idle. And for this graph, it looks mostly fine. But you notice like there is actually a gap here. It's not negligible. It's like 48 milliseconds. And what happened? Well, when I usually look at this graph, my usual guess is like for every X step, let something special happen. So if you can just count. For example, here is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's like, it seems like in every 10 steps, something special happened that block this overlap. And this is usually a good hint. Let's just go back to the code. Then you notify it here. So for every 10 step that we're trying to do an update, we print some like the debugging message saying like what's the rate, what's the loss. And because the printing that message is like blocking because you cannot trace, like you need to wait for the computation to finish for you to print a loss. And that's why we have a gap. So technically, if you want even better performance, you can increase the step to things like the 50 step or so. I believe you also don't need a step closure because the new design, you can just print it, I guess. So that's that. So this is Trace Viewer. Trace Viewer is usually a good start for you to understanding your program from an overview. Let's also look at some of other useful tooling. Let's look at the op profile. Op profile tell you how much you utilize the device. So for example, for this particular, so this is the program, like we only have a single graph. So if you have multiple different graphs being executed, you should see like multiple this bar. So you see like the hardware flop utilization is not very high, it's only 16.7%, but the HBM usage is very high. This is kind of expected because the ResNet is actually not a compute bound model. You are bounded by your HBM. So you see like the 75% of the time is being spent on the convolution fusion, which is good. Like what you expected to see is the majority of the time is being spent on the actual compute. It's either convolution or it's a memo. It's actually on the memo on the TPU is also going to show up as convolution fusion. And then you see like the 18% is being spent on loop fusion and copy data formatting. So this actually looks fine to me. The majority of the time is being spent on compute. And let's look at the memory. It's memory profile. Okay, so here is a funny part. So you see like in here, like the TPU V48, it actually has like the 32 gig HBM, which is what it shows here. It shows stuff here. If you remember, like we are compiling here, we start actually the execution. You see, we only use 10 gig of HBM, while the total HBM is 32. This is usually an indication that you can increase the batch size. Increasing the batch size usually achieve a better performance. So yeah, after looking at this profile, couple things you should get out, like the tracing and like the execution overlap is pretty good. The execution itself is not very flop heavy, which because it's convolution. I also show you how decoder model profile looks like. And the HBM usage is not very high. We can likely increase the batch size to make it better. So that's good. So look at profile. This is kind of information you expected to get out. All right. So ResNet 50 is probably not very interesting. So let me just add it here. Let me show a decoder only model, which I pretty much simplify from the Llama 2. Let's see. Chain decoder on base. Oh, it's not CD. Cool. So you probably want to look at the model as well. Example models decoder on model decoder. So there shouldn't be anything TORCH specific here. This is pretty much just a decoder only model. Like I said, I simplify from the Llama. I think I didn't do the math. I didn't do the Cosa mask. I didn't do the lottery embedding. But besides that, it's pretty standard. Like it has a group query attention layer. It has MLP. And there's nothing specific here besides the thing I just added. You see, like it's just I added locally. It's the profile hints. So what I do here is like I use this XP.traceMe API to add more tracing annotation to the graph. So then when we visualize like the XProv, you get more information. I didn't trace everything. I think I only traced the MS long, like the attention forward, MOP forward, and decoder forward. Then you should see like all of these like debugging message in the profile. So that's a decoder only model. So this thing that you have to add in the model code. It's kind of difficult to add if you don't modify the model code. But this is only debug only, so it should be fine. Then like this trend decoder only based.py is very similar to the trend ResNet.py. The only difference is that I use the decoder only model. It also uses fake data as expected. And then yeah, everything is the same, like you see here, long optimizer step. Like this part is pretty much a tracing. And you can do torch x-ray.sync, but you don't have to, like I explained, because you also use a parallel loader. The MP device loader will call the mark step for you for every batch. But it's probably easier to look at this way. And then I copy the thing. I copy the thing from like the trend ResNet profile that I pretty much copy all this profile logic into the trend decoder only based.py, so we can get a profile. So let's just run it. So like I said, we should do this manually. PTX-ray debug numbers. 1 second. X-ray IR debug equal to 1. X-ray HLow debug equal to 1. Then Python examples chain decoder on. And if everything goes well, it should just work. All right, the profiler already started, and I think right now it's doing the compilation. All right, seems like it's running. It's probably going to take a while for me to finish. Okay. You don't really care about the rate. It's not, you couldn't really compare one to one like this the ResNet. Let's see. Also another thing is like it's a very simple decoder only model. I only have like 2 decoder layers stack up. So just to compile faster and just get some meaningful result. Batch size is 16, sequence length 512. Like you can increase all of this if you want to. Self.config, where do I set a config? Yeah, I use the default decoder config. Actually, let me show you what's the default config. It's very example decoder. So the default config, it's like the 2-layer hidden size is 1022. Like I put it very small because I want user with only V2 and V3 can also run it. But for V4, you can significantly increase all of this parameter. Okay, great. It seems like the model is finished running. Let's check. It's in the temp profile, the debugging profile. Yeah, that's 2 of them. One is ResNet, one is the decoder only. Then let's just start the XProv again. All right. There's only 2 profiles, so it shouldn't be too difficult for us to figure out which one is which. I hope this one is a new one. Please be. It should be pretty obvious once I see the trace. All right, I am relatively sure this is the decoder. So, yes. So, okay, let's see. It's very similar to the ResNet in a case that you see like there's a long compilation. You see here that it's compile for the first step and just executing. If you're going down, I believe in the very end, it also show you how the tracing is happening. Probably not too much. I didn't mark all of this. So what is this? Pretty much like this part is on the CPU side. This is being recorded on the CPU side when we're actually executing the decoder layer that forward. Like you see here is IMS unknown, like the GKV, MLP. So this part is the tracing part. It happens like you can see in the PT main thread. So like I said, like we are doing the tracing and with execution. This is likely tracing for this step. So you see in the previous step, like execution already is starting while we are tracing for the next step. So this way, the tracing itself is not, it doesn't block the device execution. So everything is async. And now let's take a look at the more interesting part, which is the device execution. What exactly happened here? Well, you see, because I didn't annotate everything, you can only see some of the stuff here. Yeah, there's a lot of copy. I think they are not as interesting. Here, it's 18 more. So I believe here, like this is the group query attention that forward. So all of the corresponding fusion of above, you can consider them as computing the group query attention forward. And then you see this whole thing is in the decoder layer that forward. Like I said, I didn't annotate everything. So that's maybe like the IMS known is missing or like some layer doing additional. You see here a lot of copy. And the MLP forward, I believe is here. So fusion.59, this one is likely actually doing the actual memo. So this is batch, this is sequence, this is likely the intermediate dimension. So the whole idea is like for all of this like additional annotation, it's easier to visualize what exactly is compiler is doing, because after the compiler finish the optimization, a lot of operation become fusion. So it's difficult to tell what exactly is compiler doing. With this annotation, like at least you know, okay, in here is execute attention, in here is executing MLP, and you can kind of visualize whether the time makes sense. It kind of makes sense, right? Because like in the for this particular case, in a decoder-only model, like MLP is usually more expensive than attention. Then if we look at like the op profile, you can also see like the flop is actually a lot better. Instead of like the 12-ish on the ResNet, like the flop is 38. Let's click it. And the majority of time is being spent on convolution fusion, which is actually just memo. A memo is lower into convolution fusion, like on the TPU. And like the HBM is actually higher, like for this convolution fusion. Okay, then the next thing we look at the memory profile. Yeah, the heap size is actually increasing a lot. Like the stack is only roughly like the 15 gig. But I do believe it's because like the X-ray compiler sees like there's a lot of free memory, so it decides to utilize them. I believe there's actually a lot of space for you to increase the batch size or just increase the hidden dimension. I think it will still works. So a rule of thumb, like for like the optimizing the PyTorch X-ray model on TPU is that you just keep increasing the batch size until it show your OM error. So that's more or less all I want to cover in this meeting, in this talk. So let's recap. What did we cover? We cover how to install a PyTorch and PyTorch X-ray, whether it's nightly or it's release version. We show a very simple addition multiplication example, which demonstrates how do we do the model tracing and how do we do the model execution and what is triggering the model execution, which is either accessing the value of the tensor through things like print, or you put that in a if condition, or just more regularly, it should be triggered by something called TorchXray.sync or xm.markstep. And then we go over the change you need to make your PyTorch model to be compatible on the PyTorch X-ray, which pretty much like you move your tensor to the X-ray device. Ideally, you also want to add a parallel loader, and then you add the TorchXray.sync at the end of each step. so it knows like when to start the execution. And we cover some of the profile understanding from both the ResNet 50 and a decoder-only model, and what to look for and like what to expect. The most important things we should expect is like in the trace viewer. Let's go back again because this is very important. You want to make sure you are utilizing the device well, which means like in the top part, you want to see like there's a continuous execution and there's no big gap between. If that's a gap, that means that device is idle, which means you waste a lot of time just doing nothing. The general solution for like you see the idle time is figure out where the idle is coming from. The two common cases either like the tracing is taking longer than the execution. That usually happens when the batch size is very small because the tracing time is constant no matter how much you treat the batch size. If you think about it, tracing time pretty much is you just execute the Python code, the PyTorch Python code. It doesn't really care how big is the batch size, but batch size is the larger batch size will make the execution takes longer. So when you figure out like this Py's tracing bound, increasing batch size usually helps. And another scenario is being blocked by some other event. One common one is the data loader. So your model is data loading bound. So even the execution is very fast, but like we cannot feed like the data fast enough, so device is idle. So then you need to figure out how to optimizing for the data loading. This part is actually not a PyTorch specific. Honestly, for the most part, if you can see an XProv that looks like this, where device execution is pretty continuous, you are already in a very good start. Then you should look at the op profile and like look at the HBM usage and see how much can you squeeze out. Like, is there something unusual? Like, is majority of time being spent on a memo? If it's not, like, what is it being spending on? And how can I make it better? So that covers everything I want to talk about today. I probably will have another session talking about how to do like the model parallel, data parallel, and what kind of stuff you to look for like in the profile. But for today, thanks a lot. See you next time.